Hello, everyone. My name is Jana, and I'm really grateful to be part of this workshop. I have a background in astronomy, but recently I'm more focused on education and a little bit of outreach. And today I will talk to you about how we can bring photometry and connect it to galaxies into the classroom. So it is a practical activity that can be done with fairly cheap and accessible materials, and that can help us to inspire younger students to care about the sky and the methods of working with data. Why is photometry important? Well, it is the most important and most common way of determining all of the things we know about the celestial objects. So we take the light, we observe it, and then we measure exactly how much light has been detected. But it's not just simple like that. What we do is we divide the image, like you see here, in the three channels, red, green, and blue. But of course, we divide it into many different ones. But the idea is, instead of taking all of the light that comes from the object, we just take a part of the spectrum. So we take a certain range in wavelengths, and we only let this light pass through. And we can see that even here in these three bands, three filters, that the differences are visible, and some details that can be seen in one image are absent in the other. So this means that the objects have something to tell us with the different colors, and it can help us to determine their temperature, composition, etc. This is something that is very connected to optics, but it's difficult to teach because to get to this point of having these pictures takes a lot of data reduction and telescope time, and it's very demanding and very data and software heavy. So what I propose here is a simple exercise where we just take the filters. So for a filter, we take a simple plastic sheet that can be see-through, so we can let the light pass through. And the exercise here has not been tested with students yet, but when I did it myself, it was a fascinating experience to be able to look at a light in a different color through the filter. So looking at a red lamp through a red filter, or looking at a blue lamp through the red filter, is very interesting. And also looking at the objects in different colors, it's just very visual and can have a strong impact. And it can start to talk about the color index and how the different properties of the galaxies come up if we look at it at a different light. So this is an opportunity to extend the exercise to younger students, just for a visual effect, to see what happens when you look at it through a filter. What I suggest is to have a setup like this. The tripod is very necessary because it helps to reduce the data manipulation. You don't have to edit all the photos to have the objects in the same place, so it saves a lot of time. And then you have the camera, which can be any camera that you can have the same settings for the duration of the taking of the photos. So you can keep the exposures the same, the ISO, white balance, so this manual or pro mode of the camera. And of course, you need a lamp. I use an RGB LED lamp, so one that can change color with remote, but any different lamps in different colors would be good for this exercise. And to make it an extended source so that we don't have these images that I just showed of the lamp, I use the diffuser just so it looks more realistic, more close to a real galaxy. And here are some of the images that I got. Here is just the lamp with the diffuser. So this is our simulated galaxy. And these are the three images taken with the RGB, red, green, and blue filters. So these are saved as JPEGs, and you can see that the difference is immediately visible. Very little red light between the green and the blue. You can see there is something, but it's not very specific. It's just you can see some qualitative difference. In order to get it more precise, we can use this software, ImageJ, which is free and relatively easy to use and has a lot of YouTube videos explaining how to use it. But the steps are simple. So first, I converted the images to 8-bit so that it takes in a lot less data and it's a lot easier to manipulate. So instead of having the original photos, because they also come in RGB slices, so the camera from the camera directly gives these 3 slices. So I completed one with all 3 of them together, just have a map of different pixels with different colors, and then combine them in a stack. So I took the photo from the red filter, photo from the green filter, and the blue, and put them together in one stack, just with this command here. And the next step is to actually do the photometry, which is to select the aperture, and this is a second ring that detects the sky. So in astronomy, different conditions would give different sky background, but here it's just dark because I was able to darken the room. And the difference is calculated as a count. So how many photons, how many electrons technically on the camera can be seen in this image. And the file can be exported as a table, so then it can be manipulated in any spreadsheet software. And this is what the data looks like. We have the counts in RGB for 3 different lamps here. I give as example. These are the three colors. And we can see that they are very similar to some galaxy types. So the red one is supposed to be an early type or maybe a very dusty spiral. The bluish white one is like normal standard spiral, and the blue one is a starburst, one that has very young stars inside. And these indices here are called color index, and it's just the logarithmic difference of the counts. So these are some values that can be checked, and some objects in the literature can be found to compare if it's a realistic number or not. Some of them are, some of them not. Of course, this object is very red, and it's not. They're not galaxies that are that red. Another, I would say, fun, entertaining thing, and also very enlightening, is to make the composite images. So take red, green, and blue channels, give them the actual red, green, and blue colors, put them together to get the beautiful images that are seen every day as these astronomical images. Most images that we get are just black and white monochrome, and to get the beautiful images that we see every day from the sky, we need to combine them. I'm not very good. Somebody who knows Photoshop or other editing software would do this much better. This was just the automatic composite image from ImageJ, but this can be done a lot better to get how it would look and to see more details. So to wrap everything up, I would like to say that this is a very interesting visual and inspiring exercise, because we can actually see what is happening. We can put the lamp, we can put the filter, and it's not something that we normally are able to do in astronomy. So we can take it inside the classroom. We can take the sky inside our classroom, and we can adapt it. We can use this to simulate maybe stars or other objects. And of course, we can teach a little bit more about how the astronomical data is obtained. So how we actually get the images from the telescopes, how we work with this data, how we get the information about the objects, and of course, the beautiful images that I mentioned in the end. Of course, this exercise can be updated so that it's more suitable for younger or older students. For example, as I mentioned, as a purely visual exercise for younger students, or maybe some very data-focused exercise for advanced learners. However, I do think that bringing these kind of experiments would really brings astronomy to larger audiences, and I do think that it would inspire them to think of something think of astronomy as something that can be accessed by everyone. Thank you so much, and I would value your questions and feedback if you have any.